Hello student, good morning. I am Dr. Ajay Kumar Sinha. Today I am going to discuss compressibility factor. This is in continuation with the last class. Van der Waal equation I have derived. This is in continuation of Van der Waal equation. Now I am discussing compressibility factor Z, capital Z. Its symbol is Z. What is Z? That you understand. Compressibility factor Z, which is the ratio of product of PV and nRT. PV is equal to nRT, we know. Then ratio of this two, PV divided by nRT, that is called Z. For ideal gas, Z is equal to 1 at all temperature and pressure, because PV is equal to nRT. The graph of Z versus P will be a straight line parallel to pressure axis. Pressure is on the x-axis. For gases which deviate from ideality value of Z, deviate from unity. This is important things. For gases which deviate from ideality value of Z, deviates from unity. At very low pressure, all gases shown Z is equal to 1 and behave as ideal gas. At high pressure, all the gases have Z greater than 1. These are more difficult to compress. At intermediate pressure, most gases have Z is less than 1. Three things I have told you, that for gases which deviate from ideality value, of Z decreases from unity. Okay, this is the important point. Three things here you have to understand: Z is equal to 1, and second, Z is greater than 1, and Z is less than 1. For ideal gases, Z is equal to 1, and at high pressure, all gases have Z is greater than 1, and these gases are more difficult to compress. And at intermediate pressure, most gases have Z less than 1. These three things you should keep in mind. Thus, gases show ideal behavior when the volume occupied is large, so that the volume of the molecules can be neglected in comparison to it. Volume of the gaseous molecules itself can be neglected if volume will be large. Okay. Thus, gases show ideal behavior when the volume occupied is large, so that the volume of the molecules can be neglected in comparison to it. In other words, the behavior of gas becomes more ideal when pressure is very low. Up to what pressure a gas will follow the ideal gas law depends upon nature of the gas and the temperature. The temperature at which a real gas obeys ideal gas law over an appreciable range of pressure is called Boyle's temperature or Boyle's point. the temperature at which the real gas obeys ideal gas law over an appreciable range of pressure is called Boyle's temperature or Boyle's point. Boyle point of a gas Boyle point of a gas depends upon its nature. Okay. Above their boil point, real gases show positive deviation from ideality and Z values are greater than 1. The forces of attraction between the molecules are very feeble. Feeble means less. F-E-E-B-L-E. Feeble means less. Below Boyle's temperature, real gases first show decrease in Z values with increasing pressure, which reaches a minimum value. On further increase in pressure, the value of Z increases continuously. This explanation shows that at low pressure and at high temperature, low pressure means more expansion of gas, volume will be more, and high temperature means again gas will expand. Okay, in both gases that volume will be more. Then in that way volume of the gaseous molecules itself will be negligible. And in the by this explanation show that at low pressure and at high temperature gases show ideal behavior. These conditions are different for different gases. More insight is obtained in the significance of Z if we consider the following derivation. The means Z is equal to P volume of real gas or PV real divided by nRT. It is just like compressibility only. Compressibility is Z is equal to PV divided by nRT. Here also same things. Z is equal to PV real divided by nRT. Only volume you are considering for real gas, or what is the actual volume of the gaseous molecules. Actual volume. You know that real gases have more volume of molecules itself in consideration with real gases. Real gases are negligible, but here it is not negligible. They have some value. That's why PV real divided by nRT is also called Z. If the gas shows ideal behavior, then that time what will be the V? Then that time PV is equal to nRT, then V is equal to nRT upon P. Then this volume, or you can say this nRT upon P, nRT upon P is equal to V ideal. We are writing here now V ideal for the ideal gas, V ideal. Then nRT upon P, this value we are keeping or putting in the above equation, that is Z is equal to PV real divided by nRT. Then here P nRT, that value, for that value we are keeping as V real. Then on putting this value of nRT P in the above equation, then Z will be equal to V real divided by V ideal. P nRT will be cancelled out. Okay, and you will get Z is equal to V real divided by V ideal. It is a comparison how much that V ideal is more than V real. V real is more, then how much? That's why this ratio is telling about that things. That is also called Z. Then Z you can express in two ways. Z is equal to PV divided by NRD, one way, and other way Z is equal to V real divided by V ideal. From the above equation, we can see that compressibility factor is the ratio of actual molar volume of gas to the molar volume of it, means ideal ratio of both. If it were on ideal gas at that temperature and pressure, means if temperature and pressure were same, that time what was the volume for both, for ideal gas and for means molecules in ideal in real gas and molecules in ideal gas, volume of molecules of real gas divided by volume of molecules of ideal gas. Okay, when temperature and pressure were same, then this Z tells about same things. Okay, that is also called compressibility factor. Today I am stopping only here. Again we will discuss later on.